Okay, welcome to our second invited talk. It's my great pleasure to introduce you Tal Linzen. Tal Linzen is an assistant professor of linguistics and data science at New York University and a research scientist at Google. Before moving to NYU in 2020, he was a faculty member in Johns Hopkins University, a postdoctoral researcher at the École Normale Superior in Paris, and a PhD student at NYU. At NYU, Tal directs a computational psycholinguistics lab, which develops computational models of human language comprehension and acquisition, as well as methods for interpreting and evaluating neural network models for language technology. His talk title is Sensitivity to Initial Weights in Out-of-Distribution Generalization. Ladies and gentlemen, here's Tal.
Right. Yeah, great. Thanks for the introduction and for having me here for this massive turnout. I was trying to think what I can talk about for this workshop, and I thought I would use kind of variability due to initial weights or just other random aspects of the training process, and then excuse to talk about the things that I like to talk about, which is generalization out of distribution. So there's going to be maybe 20% methodological stuff that's related to the workshop, and 80% look how interesting generalization is and why it's important. I think that there will be hopefully some insights from both aspects of this talk. Okay, so as I think we're all familiar with the classic IAD. What does the IAD stand for? Independent and identically distributed, right? I think that's the acronym. So the way that typically people set up problems in ML, they collect some sort of data set, let's say from crowdsourcing or whatever. And then we have n examples from that data generation process. And we randomly split them into a training set and a test set. And then we train our model on the training set and see how well it generalizes to the test set. And that gives us an estimate of the generalization error of the model that we trained. So I think that when I started talking about these things a few years ago, maybe not everyone was convinced, but maybe at this point, everyone is convinced that it's important to explore generalization outside of the distribution that the model was trained on. And there are a bunch of reasons for that. First of all, it's very hard to know in advance where we're going to want to use our model, because the circumstances change from when we trained a model to when we test it. And there's the additional issue, which is that the data sets that we train our models on often have certain statistical issues, what people refer to as spurious correlations. And then when that happens, what the model ends up learning from the training set generalizes well to the test set because they came from the same generative process, but doesn't really do what we think the model should be doing. So there are good reasons to study out of distribution generalization. And the reason that I am personally really partial to is that I want to understand human language acquisition. And human language acquisition, there's a massive generalization challenge because we train our babies on a much smaller training corpus than we train T5 or GPT-3 or all those massive models. So whereas for GPT-3, you can make the case that when you give the model the entire internet, everything is in distribution generalization. That's definitely not the case for babies. So for me personally, out of distribution generalization is really crucial. And the other issue that I mentioned before about spurious correlations is that we want to make sure that the model is really learning what we would like it to learn and not whatever patterns it can find in the training set that are accidental properties of the training set, because it's very hard to create a training set that is perfectly matched for all possible confounds. And what we'll see today then, when we test the neural network's performance, on auto distribution generalization, we tend to see much greater variability than in distribution generalization. This is something that I think is not always appreciated. So everyone knows that neural networks, when trained with stochastic gradient descent, at least, are sensitive to some extent to the initial weights and potentially to the order of examples that the training set is presenting in. We know that it's a non-convex optimization problem, and there's no reason to think that we will always land in the same minimum. So the SGD will lead us to different minimum every time we restart it on a different initial weight. But I think what is underappreciated is how qualitatively different the auto distribution generalization patterns of these minima can be, even if they generalize to the test set relatively similarly. So it's not going to be exactly the same, but we'll see that the variability on in distribution generalization is much, much less than auto distribution generalization. I'll try to have some takeaways from this talk. That's often an advice that you get when you prepare talks, that there should be something that people will take away from it. So one is that we should take this variability into account when we create our models and also when we analyze them. So whatever results we obtain from using auto distribution generalization to understand what the model is doing might not generalize if we just restarted the training process again. And I'll also talk about a few resources for studying this issue that hopefully will be helpful to people. One is a data set of BERT, the kind of classic BERT release from the original BERT release from Google that we fine-tuned 100 times on MNLI, and we hope that people can just download those 100 fine-tuned BERTs and have a standard data set that people can use to analyze the variability in distribution generalization. I'll talk about the MultiBERTs project from Google, which basically is a release of 25 pre-trained BERTs. So here I was marginally involved in this project, but people pre-train BERT 25 times, starting from different random seeds on the same data set. And I'll also briefly mention a procedure for statistical comparison of two models that takes into account the variability in random seeds. Those two last bullet points are from a Google paper that was just presented at iClear a couple of months ago. Okay, so let's start with the project that exposed some variability in human language acquisition. Again, as I said, I'm going to kind of use this as an excuse to show you maybe an aspect of my work that is maybe not so visible in this community. So I thought it could be kind of a fun adventure for us. So the generalization issue that humans face in language acquisition is basically what most of modern linguistics is concerned with, right? So what when syntacticians, semanticists come up with theories of how people represent natural language, they're usually concerned with how people generalize from the very limited exposure that they have to language to these pretty arcane and strange syntactic or semantic patterns. This is just one example of a parasitic gap. Maybe you've heard of this before. So if you take sentence 1A here and try to ask a question about it, you can delete both mentions of the book, both the book and it, from the sentence, and then you add a question word, what. So this is a grammatical sentence. What book did you review without reading? But the surprising thing here is that the second gap after reading is only licensed, is only grammatical in English if there's also an earlier gap in the sentence, like in 1B. So if you take a sentence like 2A, I reviewed the proposal without reading the book, you can't actually ask the question, what book did you review the proposal without reading? Meaning, which book were you supposed to read before reviewing the proposal or something like that? This is not a grammatical question in English. So this is a very nuanced and subtle judgment, and there's really no reason to think that people have any evidence for this distinction in their learning data of English. But it's a very consistent judgment. So if you ask a bunch of people, they'll all agree that 2B is not a good question and 1B is a good question. So humans are not so variable in what they acquire from natural language, even though they have presumably some substantially different training corpora. They're not exposed to exactly the same sentences, and yet they usually end up having more or less the same syntactic generalizations. So there's this robustness in out-of-distribution generalization that is a big puzzle in human psycholinguistics. So this has motivated, maybe some of you have heard of this, Chomsky's poverty of the stimulus argument. And this is basically what it has said. So because children generalize in the same way from variable training data, and children have variable brains, presumably variable initial weights, but they all generalize the same way. So that suggests to linguists, or to some linguists, that there are strong constraints on the hypothesis space that children consider when they learn language. And that explains why we all generalize in the same way. So in a lot of my research, I've used neural networks, which we all are fond of in this room, as a framework for trying to test this sort of hypothesis, kind of the poverty of the stimulus hypothesis, where you need to have some sort of innate constraint on the hypotheses that you consider when you learn language. And the reason for doing that is maybe kind of obvious, that it's an empirical reason. You take a neural network that doesn't have any prior innate constraint on what kind of generalizations it can learn about language, and it works really well in practice and in application. So that suggests, well, it doesn't immediately address the poverty of the stimulus question, because what we care about in linguistics is not applications, but these kind of weird sentences like parasitic gaps that don't arise that often in applications. But it does suggest that it's a promising architecture to at least try to investigate. So what we do is pretty simple in this kind of modeling language acquisition. We have a learner. That learner can be a neural network or any other kind of learner. We give it the data that we think children are exposed to when learning language. And then we see how it generalizes outside of the distribution. And we compare that generalization's behavior to human generalization behavior. And the assumption is that we can generalize from our learning data in a way that's similar to humans without having a language-specific bias, this strong constraint on what hypotheses children entertain when they learn language. That means that we don't have to have those constraints. And that doesn't immediately prove that children don't have constraints like that, but it does refute the poverty of stimulus argument, according to which children must have such a constraint. So it's still possible that they're constrained, but they don't absolutely have to be if a learner that doesn't have those constraints is able to learn from the amount of data that children are exposed to. So we started from a case study that's much simpler than parasitic gaps. It's asking yes/no questions. Basically, what you have to do to ask a question in English is to take the auxiliary of the main verb of the sentence, like the zebra does chuckle. You take the word does and move it to the beginning of the sentence. We're working with synthetic data that Tom McCoy, a PhD student who's worked with me for the last 5 years and is defending in a couple of weeks, created, and he likes cute animals and cute verbs. So I apologize in advance. You move the auxiliary verb that corresponds to the main verb to the beginning of the sentence to create a question. But if you just look at this pair of examples and you're not familiar with the rule, the way that I just stated it, there are many rules that are consistent with this example. So one such rule is the rule that is the correct rule of the grammar of English, which we refer to as move main. So you move the main verb's auxiliary to the front of the sentence. But the precondition to be able to apply this rule is you have to parse the sentence to figure out which verb is the main one. But for this specific example, we can also have a simpler rule, which is move first, or this sentence only have one auxiliary verb, right? So let's say we start from the left and we scan the sentence till we hit the first auxiliary verb, and then we move that verb to the beginning of the sentence. That would still work for this example. And Chomsky's argument is that the vast majority of examples that children are exposed to in child-directed speech are of this form, where the rule that generates the question is ambiguous between at least these two options, and there are definitely more options that you can think of. So the fact that children always end up learning the move main rule shows that children are biased to only consider rules that follow the parse of the sentence and not rules that follow the linear structure or the linear order of the words. So it's not that every single sentence in English has this property where move first and move main make the same prediction. So if you have a sentence with a relative clause that modifies the subject, like my walrus that will eat can giggle, if you take the first auxiliary will and move it to the beginning of the sentence, you'll get will my walrus that eat can giggle. This is not the grammatical question. But if you take the main auxiliary, then you get the grammatical question. And again, this is one of those cases where an overwhelming majority of people will prefer the first question here over the second one. It's hard to even understand the second question here. And children don't make that kind of error. So even if they're not exposed to this kind of example, or maybe they're exposed with a very small number of them, and yet they learn the move main rule. So that's, as I said, Chomsky's argument, children have this innate constraint to only consider rules that make reference to the structure of the sentence and not to the order of the words. So I'm going to go a little bit briefly about our over our experimental design and everything. This is you can find all of this in a paper that we published in Tackle in 2020, which I think is a really nice, really impressive work that Tom did here. But I'll give you kind of a taste of how this worked. So Tom created a fragment of English that all of the sentences are grammatical English sentences, but of course we can't generate all of English from this grammar. And we trained seek-to-seek networks, basically an RNN encoder that then feeds into an RNN decoder. This was work that was done in 2017, 2018. So that's why we use that technology. And we trained it only on ambiguous examples. You see where the verb here is half pink, half orange, whatever. It means that the main verb is the same as the first verb from the left, which is the case, as I said before, in most sentences in English. So we trained the model only on this sort of sentence. And then we tested it on generalization to the kind of sentence where there's a relative clause on the subject, the one that disambiguates the two rules, where the main auxiliary is not the first auxiliary anymore. So we did a really extensive hyperparameter exploration. We looked at 3 different types of recurrent units, SRN, GRU, and LSTM. We looked at models with attention and with two different kinds of attention and without attention. At the time, people were coming up with different ideas for how to implement attention. So we tried both of them. And then we trained 100 random seeds for each combination of these 2 types of architectural choices. And here are our average results. So first, I'll show you the results on the, this lag is confusing. So first, I'm going to show you the results on in-distribution generalization. So these are sentences that have the same structures as the sentences seen in training, but with different words, basically. And all of the architectures, except the simple recurrent network with no attention, generalize quite well out of distribution. So what I'm showing you here is the proportion of the times that the model produced exactly the correct sentence with all of the words. Now, if we look at out of distribution generalization, what I'm going to show you here is first word accuracy. So the proportion of the cases where the model produced the correct first word, because remember that the crucial case here, the crucial question here is whether the model moves the first auxiliary to the beginning of the sentence or the second one. And if it makes errors later, then it doesn't matter so much. Let's say if it replaces the word walrus with the word seal, it doesn't really bear on what we care about. So we're focusing on the first word. So if you look at the average results here, they're really quite interesting. It looks like there is a combination of architectural choices that gives us generalization of the sort that we expect to see in humans. So it's surprising and tentatively that suggests that there are kind of low-level architectural features that lead the model to adopt the hierarchical move main generalization, even though we didn't build any parse trees into this model. So it's so tentatively that suggests that maybe we don't need the Chomsky's constraints. If you look at the distribution of our random seeds, though, the picture that emerges is different. So in some cases, we have enormous variability. And there's some really cute outliers here. So this outlier is a really interesting one, I think, because if we had trained only one version of this model, of this LSTM with attention, and got that specific outlier, we would have been very excited because it does exactly what we want it to do. Like 1 is good here and 0 is not good. But even the model that on average generalized most closely to humans, so where the average performance was closest to 1, had this enormous variability here, right? So this is really quite different from the situation that we have with children, where there's a lot of consistency across different learners. So what this argues for, I guess, is that so we have one random seed that leads to 100% accuracy and another random seed that leads to 20% accuracy. So these random seeds lead to qualitatively different generalization outcomes. And I think that if you only look at the average performance, that gives you a much more optimistic conclusion than if you look at the distribution over a random seed. So that's why I am very glad we trained 100 of them. So it didn't start by training 100, where we started by training one or maybe 5, and then we saw that the picture is a little bit confusing. So we went ahead and just trained 100 of them, which was easier to do for this very small seek-to-seek network than for, let's say, T5, of course. But it's very important to do if you are studying under distribution generalization. I also have a few slides about the comparison between the errors that this model made to errors that children made. I'm gonna skip those slides, but I really like that discussion. So if you want to go back to that in the question session, that would be great. I see that there's a question, so we can also just do questions now. That's fun. Yeah.
So I just wanted to know when you compare the move main versus move first, one of them is ungrammatical, as you said, right? So,
yeah.
Models could really just be picking up on that and discounting is not.
Oh, the people at home can hear you. Yeah.
Hi. Yeah. So you said that the move main is grammatical versus move first is ungrammatical. And so I'm assuming you did not pre-train on like any, you did not pre-train the models to become like language models. So they're not really tell grammar.
Yeah,
but,
they're not pre-trained yet.
Right, but the architectures could still be talking about how they're not specifically generalizing to one rule, but also just picking apart grammatical sentences versus not. I'm not sure how, but maybe that's also another hypothesis.
So maybe there's one detail that I glossed over that might address your question. So we had 2 different kinds of training instances. One that was a question formation instance, and one that is just the identity kind of autoencoding trial. So the reason that we had these autoencoding with the special token identity at the end is we wanted the model to see sentences with a relative clause modifying the subject. we just didn't want it to know how to form questions based on this sort of sentence. So it's not that the model thinks that the main verb has to be identical to the first verb. We show it examples where that's not the case. We just don't tell us how to form questions based on those examples. I think maybe that's what you were asking. I don't know. But if it wasn't, we can talk about it later. Okay, so fun comparison to errors the children make. I'm gonna briefly skip this part. But yeah, I definitely would like to talk more about this project if there's interest. I just don't want to get too much in the weeds here if most people are here for the other stuff. So the other motivation to study auto-distribution generalization is to see whether our model is really learning what we would like it to learn. Basically, what traditionally has been called error analysis, right? We want to do error analysis in a systematic way, and that is the auto-distribution generalization is a really interpretable and helpful way to do that. So this is the picture that we were looking at before, where we have IAD training a test set. And at least when we started doing this work that I'm going to talk about now, the dominant paradigm was pre-train a language model and then fine-tune it on a smaller data set that gives you examples of how to perform the task. So yeah, we train a masked language model, let's say like BERT. There's a mask in the input and you're supposed to predict what the original word was in the sentence that you masked. And then you take some sort of summary representation of the sentence and fine-tune it on the training portion of the data set that you're trying to solve. Let's say the sentiment analysis or whatever. And then you evaluate it on the test portion of the same data set that's drawn from the same distribution. That's kind of the classic paradigm. And the issue that I think has become increasingly clear in the last few years, I think when we were doing this work, people were just starting to realize how bad this problem was in, I guess, 2018. So what we want the model to do is to learn to perform the task as we think of it, something like we want the model to analyze the sentiment of the sentence, or we want it to determine whether one sentence entails the other. But what it ends up doing often, because neural networks are really sensitive to the to reverse engineering the data generation process, they learn to capture that process, and that generalizes extremely well to the test set because it's the same process. In fact, it often generalizes much better to the test set than humans. But then the danger that we face with this process is that we're overfitting to the data set. So if we generate a different data set that's supposed to illustrate the same task, the performance of the model can drop quite a bit. So it's not that we're overfitting to the training set, right? We don't have this situation where the validation loss starts increasing as training loss decreases. Like the model is not overfit to the data set, to the specific training set. It's overfit to the data set that we use to train it. But if we use a slightly different data set, then whatever it learns would be completely different. So when we come up with interpretable classes of test cases that are not necessarily from the original training set, then we can distinguish those two outcomes, whether the model is really learning the task or it's learning to capture the data generation process, and then it won't generalize well to these new examples that we're creating. And the task that we did a lot of this work with is natural language inference. A lot of you can be familiar with it. You're supposed to determine whether one sentence, the hypothesis in red, is entailed by another sentence, which is the premise here in blue. In this case, the correct label is entailment. In this case, the man inspects the uniform of a figure that contradicts the man is sleeping. You see, it's like not logical contradiction, but two things that couldn't be true at the same time in the world. So that's why it's called natural language inference, so not logical inference. Anyway, so this has become one of the most popular tasks to evaluate natural language understanding, and I think for good reason. I think that if you're able to solve this task in the general case, you really do understand language. But I'm not going to wade into that debate. I know that there are people have a lot of strong opinions about what understanding means. But setting that aside, it's a pretty solid task for evaluating language models. And as I said before, we have this potential issue with identically distributed evaluation between the training and test set, where what the model ends up learning is some properties of the training set that don't actually capture the task, but just capture the training set. So specifically what we found, I'm not going to go into all of the details of this work. We found that natural language inference NLI models that are trained on standard NLI data sets end up using really an embarrassingly simple heuristic of lexical overlap. Basically, if all of the words in the hypothesis in the second sentence are also in the premise, they usually say that the first sentence entails the second. And in many cases, especially if you look at the data set, that's actually the case. So here's an example. The tall man is sleeping on the couch. That entails the man is on the couch. And that's true. That ends up working out in a lot of cases. And if you look at the data set, in a vast majority of the cases where there is full lexical overlap between the premise and the hypothesis, the correct label is in fact entailment. So something like 90-something% of the cases. So on some level, it makes sense for the model to learn it because that's the statistics of the data set. But if you look at it from a different perspective, what the model learned was not inference. It learned something different, which is helpful in solving the test set, but is not really what we wanted it to learn. So we created this data set, Hans, that has a lot of examples where the lexical overlap heuristic doesn't actually give you the right answer. Or either does or doesn't, but we created both kinds of examples. So in this case, if the judge was paid by the lawyer, it is actually true that the lawyer paid the judge. But if the doctor was paid by the actor, it's not true that the doctor paid the actor, even though all of the words of the second sentence also occur in the first one. So we can create this balanced data set with sentences that either where the heuristic gives us the right answer and sentences where the heuristic gives us the wrong answer. So these are the results that we found with BERT in that paper. BERT's performance on the MNLI test set after it's fine-tuned on MNLI was something 84% accuracy, which is pretty high. It's much better than chance. And on the examples where the heuristic works, where the lexical overlap actually gives us the correct answer, we got even higher accuracy. Right, so this should already worry us, because why is the model so confident and it does so well on these specific examples where there's a lexical overlap if it's not using the lexical overlap heuristic? That shows us that it's using the heuristic. But when we look at examples where the heuristic gives us the wrong prediction, then the model's accuracy drops. And you see that the dashed line here is chance accuracy. So the model does much worse than chance. It's not just guessing, it's actively doing the wrong thing. So it's definitely using the heuristic. And we have, in the paper, we have a lot of discussion. We have many different constructions and some other heuristics that are related to lexical overlap. So we started, especially in light of the variability that we saw in the other project, we started to be concerned about potential variability and the results that we presented in the Hans paper. So we basically did a similar thing to what we did with the question formation project. We wanted to test whether BERT as an architecture, when it's fine-tuned on the MNLI dataset, indeed has a strong bias in favor of these overlap heuristics, or maybe we just got unlucky. Maybe we found this one outlier. Remember that with the LSTMs with attention or whatever, there was one outlier that was qualitatively different from all of the other models. So we want to make sure that because we're looking at the outer distribution generalization, that we are getting robust results. So we reran the experiment with 100 random seeds, starting from the same pre-trained BERT, the one that was publicly available at the time. So that means, unfortunately, it's a common confound, I guess, when people report random seeds, is that the random seed affects multiple things, not just the weight initialization. It also affects the order in which we present the examples in fine-tuning, and it can also affect like dropout and a bunch of different things. So it's actually quite difficult to control for it. It's not impossible. We just haven't done it. And I think it would be nice if someone else examine what is the real source of this variability, where it's due to weight initialization or order of examples or something else. So here it's confounded. And we found that the results on the test set of these 100 fine-tuned models were actually quite consistent. There were the range was, I think, between 23% and 25% accuracy. So it's not nothing. There is some variability there, but it's all pretty much in the same range. But when we look at out of distribution generalization, we get quite significant variability in the cases where the heuristic makes the incorrect prediction. So when we look at the top row and the 3 different kinds of lexical overlap examples, accuracy was very close to 100% in all of the seeds that we tried. But when we look at the easiest kind of lexical overlap, the one that's in the bottom left panel here, we get huge variability, basically all the way between 0% accuracy and 60% accuracy. So one thing that we can conclude here is actually that the first model that we trained was pretty typical, because the accuracy that we had there was something 25% accuracy. So it was somewhere in the middle here. It wasn't an outlier. But we did find this enormous variability, which is much more than we had expected. So if we look at specific types of examples, I'd say you can look at the preposition examples. So here's the examples that we constructed from a grammar would be something like the judges by the manager saw the artists, and as the premise, and the hypothesis is the artists saw the manager. So again, it's like full lexical overlap, but the correct label here is not entailment. And this kind of example, we found enormous variability. Basically, some models are close to 0%, and some models are at 70%, which is pretty close to the accuracy on the entire data set. So none of the models is at 100%, but for some of the models seem to not be learning this heuristic, which is pretty cool. And then that makes you wonder whether you can maybe find those models in some other ways. But the variability is quite significant. In other kinds of examples, and interestingly, we find much more limited variability. So this was the case with the passive examples. So for some reason, BERT, when it's trained on MNLI, is really bad at understanding passive. It just like mixes the 2 arguments and can't really tell which one is the object and which one is the subject. Whereas with its inductive bias is much weaker when it comes to things like prepositions or subject-object swapping. So the variability that we see in the results here tells us something about the model's bias. Right? When the bias is strong, we see very consistent outcomes. When the bias is weak and maybe the data set is ambiguous between different generalizations, we see much greater variability. Okay, so the resources that I mentioned, first of all, Tom worked really hard to release all these 100 fine-tuned versions of BERT. And they're all available from Zenodo, which is really great data repository. I would really recommend using it over GitHub if you can, or because it's supposed to be a permanent repository, and it doesn't depend on some like corporation being kind of generous enough to fund your repo. So I think it's funded by a grant from the European Union or something. Anyway, it's a really great place to store your data in a persistent way. So he uploaded these 100 fine-tuned models, and I think that if you're interested in studying variability in out-of-distribution generalization, this should be a really great resource. So yeah, it's like there's BERT_1, BERT_2, all the way through BERT_99, and each one is 1.2 gigabytes. So it took him a while to upload everything. Yeah, I just wanted to point out that we're not the only people to notice this variability in out of distribution generalization, and kind of about the same year basically that we published our work on variability. The group from UNC Chapel Hill also did a more extensive study of different data sets, but though fewer random seeds per data set, also showing a lot of variability across fine-tuning instances. So yeah, you should look at this paper. It's a great paper. So the last thing I wanted to talk about was the MultiBERTs project. I mentioned it before. There isn't that much to it. It's this great, I guess, Google giving back to the community by using its substantial compute resources to train 25 pre-trained BERTs. So I'm going to say it later, but again, if there's I'll say it now again, if there's anyone here working in industry and can convince your manager that it's a good use of your company's resources to develop this kind of publicly available resource to make sure that the outcomes of neural network training is robust to a random seed, then I really think you should advocate for that. It's a really cheap way for the company to give back to the community. So what we did in this project, again, this is mostly the people's Stephen and Ian that worked in this project at Google. So here we see the variability of random seeds on a few of the glue tests. There is an enormous variability, but there's some. If you look at variability of pre-training seeds, when we fine-tune it on Hans when we fine-tune it on MNLI and test it on Hans, we see quite a bit more variability. Here we have 5 fine-tuning runs per pre-training seed. So it looks like the variability that's due to pre-training is very similar to the variability that's due to fine-tuning. So we can conclude from that it's not that we were working with an especially bad version of BERT that has a weak inductive bias and generalizes in widely different ways depending on how we fine-tune it. This is an issue that is much more inherent to the architecture and how its inductive bias is weak, and the things that it learns really depends on random things like order of examples and weight initialization. The paper also has an example of the more kind of demographically related out of distribution generalization, I guess. And so here we see this is the bias correlation from the Win of Gender data set from Rachel Rudinger and others. And you also see quite a bit of variability according to random seed. There's this one random seed that is a lot less biased than all the other ones. So I don't know, that's like the social justice random seed. So if we were only if all of our work on analyzing gender bias in BERT was based on this one random seed, maybe we would be a lot less concerned about gender bias in pre-trained models than if we were looking at the whole range of models. The last contribution of this paper is a method called the multi-bootstrap, and it's just a statistical test that's backed up by a really extensive proof with like measure theory stuff and like real statistics stuff. But the point is very simple. Let's say that you come up with an intervention that's meant to reduce gender bias in BERT. And you want to see how effective that intervention is. Let's say that intervention is counterfactual data augmentation. We add examples that are meant to be anti-stereotypical and kind of balance out the bias in the training set. How do you know that this intervention is effective? So here are the bias scores after the intervention. They're lower, but are they lower enough that we can conclude that the intervention was statistically significant? You see that in some of the cases, the intervention didn't do anything. Like, if you look at the this seed or this seed, basically 22 or 23, the intervention didn't do anything. In some other seeds, the intervention was very effective. So in, I don't know, seed 1, the intervention reduced the bias correlation by almost half. So what this method gives you is a confidence interval for the difference in effect size between the two methods. And also you can get a p-value out of it if you're into p-values, which some people are. So this is what it looks like. You get the confidence interval that's between, I don't know, and having some like substantial effect and having no effect. And then you also get a p-value. Okay, so this was I'm not going to tell you about this method. This was just supposed to be like a quick advertisement for it. And I guess the last thing is that there's ongoing work to do the same thing for T5. If so, watch the space, I guess. Yeah. And MultiBERTs is available from Hugging Face. So this is a very convenient, another very convenient place to put your data. If you, again, it has advantages in that it interfaces very well with the Transformers library. It has some disadvantages in that you're relying on the generosity of a corporation to keep storing your data forever, and who knows what will happen with Hugging Face when it's acquired by like, I don't know, General Electric or something. Anyway, so but it's you should use this. It's very easy to use. If basically you just plug in, if your code only uses the Transformers library, you just plug in MultiBERT seed 24 instead of BERT, and it's supposed to work. Okay, so to summarize, we saw that generalization behavior can differ qualitatively across random seeds. And I also showed you a bunch of like a taste of the type of research that we do for theoretical modeling of language acquisition. As I mentioned before, the one issue that we have in this literature is that the effect of random seed can be either through initial weights or through the order of the instances or some other maybe source of randomness, such as dropout, and that's usually not disentangled. So it would be interesting to try to disentangle them. We should avoid comparing architectures based on a single random seed. So I don't know the answer to this, but we do know that in a lot of tests, Roberta is much better than BERT. And it's kind of surprising because architecturally, they're really, really similar. They're basically the same thing. So is it the architectural choices that they made that caused Roberta to be better than BERT, or is it just a fluke? Maybe if we had 25 Robertas and 25 BERTs and compare them, we would get very similar results, and the confidence interval of the difference between them in accuracy would include 0, and then we would just not be able to conclude anything. We should also not come to interpretability, quote unquote, conclusions based on a single random seed. As we saw at the beginning, there can be qualitatively different generalization behaviors across models based on random seed. And the kind of discussion questions, I guess, and then I'll end. So it's not always clear to me that, at least from the theoretical perspective of cognitive science or analysis of models, it's better to have models that have higher average accuracy over models that are stable over runs. So we always optimize at the mean accuracy, and we'd never optimize for the variance of the accuracy. And I think it would be interesting to come up with architectures that have much lower variance in accuracy when they generalize. So accuracy, architectures that have a clear, stronger inductive bias, where when you give them the same data set, they're going to generalize in a very similar way, even if you shuffle the examples, let's say. I think that would be an interesting dimension to try to optimize architectures for. And one reason why that might be useful in practice is that maybe you don't want to have to run 100 random seeds for every fine-tuning task that you care about. Maybe you want to do the foundational work once and kind of verify that the model is robust to these random fluctuations. And then when you generalize to new tasks, you would be relatively confident that you can run just 1 seed or 5 seeds, and you know like where you're standing with this task. And as I said, I think if you're in industry, when you create a new model and it becomes widely used, it would be great if you could follow the example of the Google group that released these 25 pre-trained versions of BERT. It's not that easy technologically, even within Google, just getting the compute, and so it required a lot of work from people. But I think it's work that is extremely worthwhile. So you should do that if you can. Yeah, and that's all. Thanks for listening, and thanks for, I guess, and yeah, I can take a few questions, right? Or no? Yeah, okay.
We have time for a question.
Okay.
It's time for speaker. We have quite a lot of time for questions, so please queue behind the mic.
Yes, thank you very much for a great talk. My name is Steve Thomas from Queen's University. Yeah, this is very eye-opening for me, and it's almost a little bit alarming because it kind of calls into question every paper at ACL over the last couple of years. So, I mean, if the results can vary so much from seed to seed, I mean, is it as bad as it sounds? Like, could it be that papers are accepted only because of dumb luck? And if so, is this like inherent to BERT and transformer architectures, and the only solution is to do 25, 100, or is there some fix, statistical fix, or in the training process or something like that?
Yeah. Well, first of all, I think the situation is worse with out of distribution generalization than in distribution generalization. And for better or worse, a lot of the ACL papers are accepted based on in-distribution generalization. So if you look at the glue tasks, here the range is actually not that large. The x-axis here goes between, I know, 86% accuracy and 87% accuracy, or whatever for MRPC. Who knows what that is? So I don't know if it called into question everything that's been done at ACL. It is possible that some results are due to dumb luck, and that's I think why we think it's such a good idea for people to evaluate their model against these 25 MultiBERTs. So, by the way, just to clarify something, you don't necessarily have to train 25 versions of your model to compare it to BERT. So if your model falls somewhere between the in the range of the MultiBERTs, then it's likely that it is not going to generalize better than the MultiBERTs unless you got really unlucky, right? So I mean, it still would be a good idea for you to train 25 seeds, I think. The answer to the other question is that I don't know. I think it would be really interesting to have models that are more consistent and more robust to random seeds, but I don't have the right answer for that. I think that in general, the stronger the inductive bias of the model, the more consistent it's going to be in generalization. And the examples that we have where we built syntactic trees into the model, for example, and that caused the model to generalize in a much more consistent way. So that's one thing that we can try to do, but I don't know what the kind of statistics, ML, deep learning answer to this problem is.
Okay, thank you very much.
Yeah.
Hi, thank you for the great talk. So I had a question related to the loss landscape perspective of this problem. So most work, when we talk about in distribution generalization, they try to relate it to how the model converges to, say, flatter minima or a sharper minima. And even when we talk about weight initializations and like the conditioning of the Hessian and so on. So is there any similar intuitions when we talk about out of distribution generalization? Have you seen anything similar?
Yeah, that's a really great question. I haven't worked on this, but if you can find Naomi Safra from NYU, postdoc at NYU, they have a paper that's in submission at NeurIPS, I think, and is looking at exactly that question. So when I was preparing this talk, the paper was not really ready to cite, but I think that it's a really interesting question, and it's worth looking at that paper. Safra, it's like SAPHRA.
Okay, cool. I'll look it up. Thank you.
Hi, thanks very much for a very interesting talk. I am just kind of getting into this whole using pre-trained language models and fine-tuning. And from my understanding of the field, the small size of the data set can have a huge effect on stability, and that kind of random seed variation is much more noticeable. Do you think that's related to the generalization problem that you're, or the in the out of distribution generalization?
Yeah, I guess that well, first of all, most of the results that we presented were on MNLI. MNLI is quite big. It has 300,000 examples. So as these NLU tasks go, it's one of the biggest one. But I do know that when the fine-tuning data set is small, you have more variability. I think that the distinction between in distribution and out of distribution is a little bit artificial. Basically, there has to be a spectrum, because if you fine-tune the model on a single example from the training set, everything is going to be kind of out of distribution when you analyze the test set. So I think it makes a lot of sense to me that when the training set is small, more of the generalization would be of the out of distribution kind. Basically, you need to know things that the training set doesn't teach you well. Yeah.
Thank you.
Is there any question from our virtual audiences? Thank you very much, Tao. This was very interesting. So let's have a warm welcome to Tao.
Thank you.